Hi, in this video, we want to take a look at the multinomial distribution. Okay, so this is really going to be an extension of the binomial distribution. So remember, when I'm talking about the binomial distribution, we have repeated trials, such as like flipping a coin, and in binomial situation, we have two possible outcomes. Now, on top of that, we make the assumption that the probability of each event is constant, and we have independence between events. So that's saying that I flip a coin a known number of times, a fixed number of times beforehand. There are two possible outcomes. The probabilities stay the same no matter how many times I flip, and the events are independent of each other. All right, so now we want to extend this just a little bit. Now, once again, I'm going to have a predefined number of events. I'm going to have independence between events. I'm going to have constant probabilities. But now I have two or more possible outcomes. Okay, so it could be I could have three possible outcomes, four possible outcomes, 50, whatever we potentially would want. And so this is going to be the multinomial distribution. Okay, so if I take the multinomial distribution and I set k equal to 2, then I end up getting the binomial distribution with just a little bit slightly different presentation, but it ends up being the same. Okay, so the multinomial experiment, this is the assumptions that we have for us to be in a multinomial situation. We have n identical trials each time. So here, this is the like number of times I'm going to flip the coin, number of times I flip the coin. We have k distinct outcomes. Now, the probability that each trial lands in a particular outcome is, we're going to say p sub I, and I goes from 1 to k. Now, the probabilities are constant from trial to trial. Of course, probabilities add up to 1. The trials are independent. And for us, the random variable of interest are the counts of the number of times that we see each possible outcome. Okay, so if it was binomial, I'm interested in the number of times I get heads and the number of times I get tails. So x of 1 would be the number of heads, x of 2 would be the number of tails. Okay, so when I add these all up, I have to get the number of trials that I have. Okay, so now let's go ahead and actually look at the mathematics. Now, this is a pretty ugly distribution formula, but it's not that hard. It's a lot slicker, a lot easier than we think it is. Okay, so what I've got going on is I want to know the probability that I get a particular number for the first outcome, a particular number for the second outcome, particular number for the third outcome, and all the way up to the kth possible outcome. All right, so the probability is going to be the probability of the first outcome to the power of the number of times we see it, times the probability of the second to the power of the number of times we see it, probability of the third to the power of the number of times we see it, and keep on going, and we multiply it out. Now, if you think about it for a moment, I could, if I was doing the binomial distribution, I could have heads then tails, I could have tails then heads, right? Now, for the purpose of counting, that's 1 each. Either way, there's 2 ways to get that same outcome. Okay, so I need to make an adjustment for the number of ways I can get a particular outcome, because we don't care about the order that we see the outcomes. We just care about the number. And so here, this ugly fraction with a lot of factorials addresses that. So I have number of trials, factorial, divided by the number of times I see outcome 1, factorial, number of times I see outcome 2, factorial, number of times I see outcome 3, factorial, and so on and so on. All right, so remember, if I add up all of the counts, it adds up to n. If I add up all the probabilities, it's equal to 1. Now, what's the expected value of the number of times I'm going to see outcome I? Well, it's going to be, this is going to look a lot like the binomial distribution n times the probability of seeing one particular one. Now the variance, well, it's going to be n times p times q, where instead of p, it's piece of I, and q is 1 minus piece of I. And now here, remember, I've got multiple things going on. So I've got a covariance aspect, and my covariance is n times the product of the probabilities that we're looking at. Now remember, in this one, when I talk about covariance, I and j cannot equal each other. Okay, so let's go ahead and hit an example using R. Okay, so what I'm going to do, I want to show you that this distribution is in fact the correct distribution. I'm not going to talk about how we get that. It's actually really simple using polynomials to the power of n. It's very straightforward. If you're a math major, it's like one of the easiest proofs you'll ever encounter, but I'm not going to do it in this video because I'm not intending this for math majors. Okay, so what we're going to do is, let's go ahead for this example. Let's say that I have packaging of items, and let's say I've got 4 items per box. And now when I go through, I do my quality assurance checks, it's possible that each individual item either has no defect, or a type A defect, or a type B defect. All right, so I have 3 possible outcomes: no defect, type A defect, or type B defect. Okay, well, so this is going to be a multinomial distribution because I have 3 possible outcomes, and my number of trials is equal to 4. Now, the probability of the defects is really, really high. I picked these numbers to make it mathematically easier to look at. So that way we're focused more on the concept and not on the individual numbers. So if that seems really high of a 30% defect, yeah, that is. That's really high. But all right, so let's go ahead. I want to go through this code, and I want to generate some random observations just so I get a feel for what's going on. So what we're going to do, each time I have my multinomial event, I have 4 items being checked. And to generate my random data, I'm going to generate 10,000 random samples just so that we get a full distribution. Now here we've got no defect, defect A, or defect B. And I'm going to write this as a factor just so I have control over the order of things. Now I'm going to generate my sample. And here I'm using the sample function in R. So I'm taking no defect, defect A, defect B. I'm getting 4 times the sample size, 4 times the number of samples, number of observations. And of course, I'm sampling with replacement because it wouldn't make sense otherwise. And here are my probabilities: 70%, 20%, 10%. All right, and then I reshape it into a matrix using the matrix function, and then I put it as a data frame just so I've got everything worked out. Now, what I'm going to do, I need to make sure that everything is in a factor. Why do I need this as a factor? Okay, well, in a moment, I'm going to use the table function to count. And the times that I have 0 for a particular level, specifically defect B will occur the most. In R, if I do a table on a character string instead of a factor, what it's going to do, it won't count those 0 cases. It will just go only with the observations we have. And I don't want to drop my zeros off of this one. And so here I go through, I use lapply to generate a list of each sample I'm converting to a list where it's a factor, and then I go through and I get my counts using the table function, and I use as vector just so that I have the right format, just so that under the hood our things work out. And then I convert it to a data frame using dplyr to put everything on top of each other, to stack it. Okay, so let's take a look at our actual sample. All right, so in this situation, I looked at the first box and no defect, no defect, no defect, no defect. That's a good box. Now, in the second box I looked at, no defect, no defect. The third item I picked up and looked at had defect B, and then no defect. Now, the third box I looked at, there was no defect. The second item I looked at had defect A, then the other two did not have a defect. And then the fourth box I looked at, I had defect A in the first one I checked. The second one I checked had defect A, and then there were no more defects. And then so on and so forth. Now, when we're in the situation, if I'm talking about the multinomial distribution, I actually don't care about these particular values. These are not important to me. I don't care about the actual data I have. I care about the counts, because the multinomial distribution, that gives me probabilities of the counts, not the individual samples themselves. So when I look at this, if I look at the counts, I'm looking at the table values. And I can see that for the first one, it was 400 because I had 4 no defects, 0 defect A, 0 defect B. On the second one, I had 3 with no defect and 1 defect B. Notice when I have a table representation, I don't care about the actual order of which I came across things. I just care about the total counts of what I observed. Okay, so now what I want to do, I want to take this sample, I'm going to get my empirical frequencies, and I want to compare that to the theoretical frequencies. That way, you believe me that this is the correct way to count this, that this distribution is performing as advertised. All right, so what I'm going to do, I'm going to generate all the possible combinations that I could get, with a total of 4 counts in each row. So what's happening here? There's a little bit of inefficiency here. If I use combinatorics, I can make this computationally efficient, but I want just something, I want more compact code. So I chose this way. Professor Bona, please don't hate me for not using combinatorics. Professor Bona taught me combinatorics in Gainesville. All right, so here what I'm doing, I'm taking all the values, 0 to 4, 0 to 4, 0 to 4, and I'm expanding the grid and getting all 4 to the power of 3 possible values. That's what, see, is it 256 or 120, 128, I think? Yeah, probably. Okay, something like that. All right, so it's pretty big. Now, the thing is, this includes counts that we can't have in this situation. We're only interested in the cases where we have exactly 4 total outcomes, where the rows add up to 4. So on the next step, I filter it out like that. So here I go out and I filter it down to just 4. Now, what I'm going to do is, or this step is just to give me row names that are a little bit more informative. You really don't need this, but I think it looks better in the presentation in a moment. Now, on this step, this part of the code, I'm going to go through and I'm going to count the number of times my data set, my observed values, give me the same counts as in my my possible values. And so this is just figuring out the number of times I have the corresponding counts for each observation, and then I add up all the times it works out. And here I am rescaling to make sure that I have a probability value. That way I can compare my observed probability with my theoretical probability. Now here, on this part, I'm going through and I'm doing the computations of the theoretical probabilities. So here I've got that factorial of n. Here I've got I've got each probability to the power of its count. and I'm dividing by the factorial of the counts. And then I'm doing multiplication. Okay. And now on this step, I go ahead and I sort the values, highest probability to lowest probability, just so that it's easier for me as a human being to interpret what's going on. So now let's look at our outcome. Okay, so here I can see that this column is no defects. Number of times we have no defect, number of times that we have defect A, number of times we have defect B. If you scrutinize this, you'll see that I have all the possible situations here. I double checked this manually, by the way, before I made the video. Now here, this is from my data set, my observed probabilities, and here are the theoretical probabilities. All right, and you'll notice that they are matching up very nicely. They're very close. Now there's something surprising in this. Okay, you'll notice that if intuitively, if 70% no defect, 70% no defect, so that is the largest probability of a particular outcome, I expected naively to have 4 no defects as being the most frequent observation. And I also, made the assumption that 4 defect Bs was going to be the least likely outcome. Now, I was right about 4 defect Bs, very low probabilities, but when I look up here, I can see that the probability of having 3 no defects and 1 defect A is in fact the most likely. I was surprised by this. Why is this? Like, yes, the probabilities, if I just consider the probabilities themselves, this one is going to have the largest probability, but that's not taking into the number of different ways we can get this. There are 4 different ways that I can have 3 no defects and 1 defect A. And so because of that multiplication, it pushes this probability to be greater than that probability. Therefore, 310 is the most likely outcome that we could possibly have. Huh. I mean, that's kind of interesting, right? Okay, well, that's all I've got for you. Take care and goodbye.